One thing you can do in the meantime is there's a practice midterm on B courses in the homepage. You can look at that. We're gonna see some of that material, and we're gonna see some material from another practice midterm. And if you have questions that you already want to ask, conceptual questions or questions about the midterm kind of logistics, you can ask them in the chat. I'll repeat all of this at 1:10, but if you want to get ahead. All right, everyone. It's 1:10, so I'm going to get started. So welcome to the review session for the second midterm, or the first quiz of the second midterm. So we have about 50 minutes. So what we're going to cover is transformer for about 20 minutes, transformer / NLP. And then we'll talk about adversarial training. We'll talk about GANs. We'll talk about VAEs. And then we're going to kind of like go over, for each, we're going to kind of go over the main facts and the main components of the models, and then do a problem usually. And then what I want to do is, if you have questions, you can ask them throughout. And if you have a question but it's not particular to a specific topic, you can keep it for the Q&A at the end. All right. So we're going to get started. The first thing is, does anybody have any questions about like logistics for the midterm? Or you guys feel good? Yeah, you should ask questions ideally in the chat. And then we're 3 TAs, so either somebody's going to answer in the chat directly, or we'll kind of give the answer to everybody. This is also going to be recorded, so you can kind of like watch it again later on YouTube. All right, let's get started. So, well, I guess logistics, just to remind you, the midterm is going to be released on Monday, and you're going to have 3 days to complete it, so that you'll have until Thursday. It's going to be, I think, in terms of amount of time it takes, it's going to be about the same as a regular midterm. And yeah, it does not cover, John has said that it doesn't cover the last week's material, so we're honoring that. So the last 2 lectures are not included in the material for the midterm. Yeah, without further ado, let's get started. And bear with me, I'm going to jump from kind of PDF to PDF, things I'm sharing. So it's going to be a bit like, if you get lost, let me know, and I'll give you some time. If you need help with something, I can give you permission to annotate as well. So if you want that, we'll go with that. All right. So we're going to start with transformer, and I want to first give you a brief reminder of what attention is, because attention is just at the center of the transformer. So it's good to get a refresher. And so for that, let me open the practice midterm that we have. Okay, so let me close this and I'll start sharing. So this is a good warm-up question. Oh, I shared the wrong thing. Give me a second. Share. Okay, it's not showing up. Well, all right, I'm sharing my whole screen. So the question, so this is a question on the practice midterm. So it says, the diagram below shows a language translation model without attention, and it says modify the design to include soft attention. So I want you guys to think about it for a second, because this is where attention first appeared, right? It appeared in LSTMs and in translation models. The main problem that was happening was that the sequences were getting too long, and the LSTM, even though it has long short-term memory, it wasn't enough, and this thing was forgetting things from the start of the sequences, if you remember. So people started building these attention mechanisms, which I call kind of highways, information highways in the network. So I'm going to just kind of answer it really quickly, but essentially, all right, essentially attention, what it does is the decoder gets to look at each of the encoder states. So this is what I would have drawn if I was taking this midterm, and I would have drawn, this would be, sorry, and it's hard for me to write, but this is A11, A12, A13, and then I would have drawn, you know, these things. Oops. No, yeah, I'm doing it right. And then chuk, right? So each state in the decoder looks at every single state on the encoder, computes attention weights that sum to 1, and then can leverage this information, the information in the encoder in the decoder state, so that now there is you know, a finite length distance between any state in the encoder to any state in the decoder, which is not the case without attention. Anybody have questions about that? So the attention that we talked a bit more about with you guys is the Luong attention. So if you want to review that you should look for that keyword Luong, L-U-O-N-G, to see a little bit more how it's implemented. All right. So from there, I want to move on to transformer, and let me kind of clear the annotations, clear all drawings. So that was for attention, and now we're going to go over the transformer diagram, because I think it's quite dense, but actually it has a lot of cool information in it once you know about the transformer. By now, you guys know about the transformer pretty well, so we can kind of try to understand. So the first thing you need to know is that a full transformer, which also appeared in machine translation at first, has an encoder and a decoder. So here the encoder is the left column and the decoder is the right column. And these two are very similar, except for the fact that the decoder has cross attention, right? So let's start with the encoder. The encoder has self attention. It has feed forward. That's what we call one layer. Within each layer, you have these residual layers. Can you guys see my mouse by any chance? Let's see if I can see the chat.
Yeah, we can see your mouse. At least
Okay,
I can.
cool. Okay, so if you can see my mouse, that's really good. So this is the residual, right? So the add here is what makes it a residual, because you add the input to the output of each layer, and then you normalize. So you have residuals, and each layer is made of two kind of blocks: the feed forward layer and the multi-head attention. We'll talk a little bit about multi-head in a bit, but here this is self-attention. The way you know this is self-attention is because there are three things going in there, and they all come from the same thing. So self, right? You'll see here that cross-attention here, you see that it's not all coming from the same place. And what are these three things? It's the query, the key, and the value. So usually what happens is the query comes from a place, and the key and value come from a different place. So here you can see that. So this is how you can tell that in this diagram, this is the query. The rightmost is the query, and then key and value are the left and the center. All right. And essentially, the big difference between an LCM and an encoder block of a transformer is that here there is no recurrence, right? So there's no causality. So just like in attention, you remember we were having these highways. Well, here every element looks at all the other elements. Oops, sorry. So that is why like kind of attention became a very important piece, is that instead of having recurrence, which is the main element in an LSTM or in an RNN, attention became like kind of the central piece, right? And the problem with that is that this loses some information. Essentially, it loses when everything is connected to everything, you lose the notion of the word position, right? But actually, when we speak English or when we deal with text, word position, which words are close to which, is really important to understand sentences, right? So if I say the cat ate the mouse or the mouse ate the cat, if I don't have positional information of the words, I can't distinguish these two sentences, right? And so that's why there is this positional encoding that essentially adds this information into it. And you should review a bit of, I'm not going to go in detail as to what the positional encoding does exactly, but it's essentially, it's giving you the model an easy way to do relative differencing. So to be able to say, okay, I am here. What are the words that are 2 away? What are the words that are 3 away? So it gives the model a pretty simple ability to look at its neighborhood of words, essentially. All right, so that's the encoder block. The decoder block, you'll see, is essentially the same thing, except in the middle, you have cross attention. And the reason for that is that when you're doing, imagine we're doing translation, right? And we're translating from say from French to English. So you're going to first encode the whole French sentence. Okay, so you're going to build a representation of that sentence. For each word, you're going to have an output. And then as you're decoding, what you're going to do is, first step, see what you've generated so far. That's self-attention. The second step is going to be look at the French sentence to essentially decide what to generate next and to get, the relevant information from there. And the third step is a feed-forward transformation, right? So kind of like transform and compile what you found into a final kind of word decision. All right, so that is essentially the one of the big differences. The other big difference is that here you can see the word masked, and that is because when you encode something, you don't need to look at you don't need to do it one word at a time. You can encode all of it together, and you can do self-attention all together. So it's pretty parallelizable, and that's one of the main advantages of a transformer. But when you decode, obviously you have to decode in a generative process means you have to decode one step at a time. And so when you do self-attention, you have to only look at things on your left, or essentially things that are generated before you. All right, so that's why here you need to use a slightly different mask for the self-attention in the decoder. All right, and one brain teaser for you guys is to think, if this is used for machine translation, for instance, here imagine the dimension of the model is say 1024 or something like that. So each layer has input and output 1024. So here at the output, just before the final linear layer, you get something that's 1024. What is the dimension of this linear layer? That's something to think about. So you have to project into something to make your decision. What should it be? You should think about that a little bit. I'll give you the answer, but if you don't get it, you should think about it. The dimension of this linear is dim by output vocab size. So for instance, if you have 80,000 words in your vocab, which was at the time of these models, that's what they were looking at, then this matrix will be 1,000 by 80,000, essentially. All right, cool. So that kind of like concludes our overview of the transformer. Do you guys have any questions? Let me check the chat. All right, it seems good. So I'm gonna keep going. So we're gonna just go over the questions from that midterm and see if we can answer them. Okay, so what is the reason for positional encoding and how is it typically implemented? All right, so I'll let you guys think about that for just 30 seconds. Or I guess I'll answer it. So positional encoding here, why is it needed? Just like I said, because usually when we're dealing with text, the word order matters. And so without word order, you would essentially, the transformer would not have a notion of which words are close to which words come before which. And that would limit its capability to model the text. So positional embedding usually is added to the input embedding. It's added on top of that word vector, which means that if you have the same word in position 5 and in position 12, so if you have, for instance, the black cat and the red cat, so you have cat twice in the same sentence, essentially the model will be able to differentiate them because even though the input embedding is the same, the positional embedding is different because the positional embedding at 5 and at 12 is different. And usually the way it's implemented, at least at the start, there's two main families of implementations. One is a learned embedding. So it's just a word matrix, just like in an LSTM. And that's more prevalent these days, I think. The main limitation of word embeddings, of learned positional embeddings, is that if you decide to have a learned positional embedding up to size 512, your model will never be able to be trained for sequences beyond 512, right? Because you won't have a positional embedding for 513. So that's why people don't really like it. And also the problem is if you have very few sequences of long length, then the positional, even though it's learned, the positional embedding for long lengths end up being undertrained because you have very few examples. So at the the implementation we talked about more, and that is in your homework 3, is a non-parametric positional encoding, which is based on cosines and sines, and cosines and sines of some fundamental frequency. And the reason they chose to do this kind of esoteric thing is because with cosines and sines of different the same but different different harmonics of the same fundamental frequency, you like the model with simple multiplications and additions will be able to have relative positional encoding pretty easily. So it'll be able to say, this is 3 away, this is 2 away from me, which is quite nice because we know that in English, a lot of sentence structure is local. So the words that are close to you are the most relevant. All right, so that's the first question. Hopefully you kind of understand that. I'm not going to draw a diagram, but hopefully you kind of see what you could do. Okay, and then this is the second question, which I said we'd talk about in a bit, which is all of these attention blocks. One of the big things that this paper did was to do multi-headed attention. So here it's multi-headed, here it's multi-headed, here it's multi-headed. And you've implemented multi-headed attention in homework 3, so hopefully you kind of have an idea of what it means, even though we make you implement it in a very neat and kind of crafty way that doesn't that is pretty fast. But essentially what you're doing is, instead of having, so if your model size is say 1024, instead of having a single head that has embedding size 1024, you're going to say, okay, I want to cut it up into 8. So I'm going to have 8 heads, each of size 124. If each head is of size 124, technically I haven't increased the number of parameters, right? So the model complexity is the same, right? But now, instead of having a single head that can only focus on a single thing, you can have heads that focus on different things and specialize in different ways. And that is quite powerful because now you can have a head that focuses on syntax, and you can have a head that focuses on finding verbs, and you can have a head that focuses on finding subjects, etc. So generally, it was shown that it's very useful to have several heads that are smaller instead of one big head. Okay, so hopefully that answers that question. There's another question that I saw somewhere else in another practice midterm, which I like, which is related to this, which is, if you're training a transformer, how do you initialize the query, key, and value projections in multi-headed attention? And it gave a few options. So it said you initialize them with constants, you initialize them with randomness, or you initialize them with, I don't remember. But essentially the right answer is to initialize them randomly. And the most important thing is that you initialize each head with a different randomness. So you shouldn't, so the heads should not all start the same, because you wanna break the symmetry essentially. If you want the heads to learn different things, you should initialize them differently, essentially. Okay, so hopefully that makes sense. All right. So for input sequences of length m and output sequences of length n, what are the complexities of the encoder self-attention, encoder decoder attention, so cross attention, and the decoder self-attention? All right, so I'm going to kind of answer that one quickly. So if the input sequence length is m, then self-attention is going to be is big O of m squared, because every single element has to look at all the other elements. So every element has m operations, and then you have m of these operations, so that's m squared. Decoder encoder attention is n by m, because for each output element, I'm going to look at each input element, so that's n times m. And decoder self-attention, you've probably guessed it, it's n squared, or you could say, if you're kind of thinking about it, it's big O of n squared over 2, right? Because each element is only looking at elements on the left, right? So it's n times n minus 1 divided by 2. But essentially, n times n minus 1 divided by 2 is big O of n squared. So you could just say that. All right, so I like this. So hopefully, does that make sense to everybody? Let me take a quick break so that if you guys have questions, I can check. All right, cool. You guys are oddly silent for a review session. And yeah, I feel like it's better if I just go over it than ask you for answers, because of the Zoom aspect. Okay, so the fourth question, do activations on the encoder depend on decoder activations? How much additional computation is needed to translate a source sequence into a different target language? So this is a really cool question. Um, it's close in practice to some things that are done. It's not exactly what you would do, but essentially imagine you have a universal embedder, right? So you want to train something to go from English to any language, right? So you embed into English, and then you have a specific decoder for French, and then you embed something in English, and you want to decode it into German. And the question is, how much of the computation would you have to redo, and how much of the computation can you keep? And essentially, what this is saying is that the encoder you would be able to keep, right? But what you would have to redo is obviously the decoder self-attention, as well as the decoder cross-attention, right? Because new language, new cross-attention, because you're going to generate in a different order. So essentially, this one, the m squared gets saved, but you still have m times n, and you still have n squared. All right, so that's for this problem. Any questions about transformers? I'm gonna go over BERT and GPT-2, but for like the transformer architecture itself. Cool. Yeah, you guys are all super familiar with transformers. That's a good thing. All right. So the next step, I want to talk a little bit about BERT versus GPT-2. And I don't particularly have a slide for that, but essentially this one is pretty good because a BERT model, what you should remember is BERT is for natural language understanding, not generation, for understanding, and it looks like a transformer encoder. So it looks like this block. All right. And then the next thing is a GPT-2 model. The G stands for generative pre-trained transformer. The 2 is because they did one and then they did a bigger one after that. Looks more like a decoder, except there's no cross attention. So it just, the only difference is that it has masked multi-headed attention and feed forward. And that one is for natural language generation tasks. All right. And so that's the first step. The second thing you should know is that BERT is trained on 2 tasks, masked language modeling and is-next prediction. So masked language modeling, the way it looks is given a sequence of words with probability 15%, you're going to replace a word with a mask token. And then on the output of the encoder, you have to repredict that word. Because there's no notion of, there's no generative process, it'll be able to look on the right and it'll be able to look on the left to make the prediction. And then is-next prediction, for those of you who don't remember, is what we're going to do is we're going to take essentially 2 blocks of text, 2 paragraphs, and with 50% chance, they're going to be consecutive in a document. So they're going to be actual consecutive documents or actual is-next document, textual documents. And with 50% chance, we're just going to randomly sample 2 text documents from our corpus, right? So for instance, a news article about France and the Wikipedia article about penguins, and we're going to stitch them together into a single input, right? And then we're going to ask the model, is paragraph 2 the next paragraph in the document to paragraph 1, right? And essentially, the model is going to learn to recognize, kind of like masked language modeling is more like token level accuracy and being able to do syntactic stuff. And supposedly the is-next task is more about semantics and being able to figure out, yes, this paragraph follows semantically from the previous paragraph. BERT is really good at is-next, as you can imagine, because it's really simple. It gets like above 99% accuracy at that task. All right, so that's kind of what I want to talk about BERT and GPT-2. One thing that I want to go over quickly is some of the tasks that you should review, like the NLP task that we talked about during the kind of applied NLP. BERT was a really big revolution for the field of NLP because it really improved, just like in CNNs, the ImageNet challenge was really important. There was this challenge called glue, so just like glue, And it was sort of 8 tasks in NLP that were seen as kind of quite different. But if one model could do good at all of them, that would be really impressive. And that's what BERT did. It kind of like pushed the limit on each one of these tasks by quite a bit. And so what are some of these tasks? So some of these tasks are, you should remember the NLI tasks. So that's natural language inference. It's also called RTE, so textual entailment. I forgot what the R stands for, but so entailment and inference are kind of like both used to describe this task. Machine translation, you should remember, that's not part of Glue. There are other tasks in Glue that are like paraphrase identification, sentiment analysis, STS, COLA, so language acceptability. We talked a little bit about each one of these. And then another big type of task that that is not part of Glue, but that got added to what was called Super Glue is SQUAD. So SQUAD, question answering, was the Stanford Q&A dataset. And that's also something that BERT was really good at. You should kind of review it and remember, like the main thing that you need to remember is that it's not an generative process. It's given a paragraph, given a question, find a span in the paragraph, extract the span in the paragraph that gives the answer. Yeah, so that's kind of all the NLP tasks. Anybody has questions about some of these NLP tasks? So BERT type, so that's BERT types of tasks. For GPT-2, the types of tasks are so language modeling in general, conditional language modeling. So for instance, generating headlines, generating summaries, generating text in different language, generating questions, etc. So anything that involves creating new text conditioned on something, you can use a GPT-2 for that. All right. So if we feel good about this, I'm going to move on. I spent, I think, 5 minutes extra on this, but that's okay. So that's the NLP. NLP is going to be a big chunk of your midterm, I think. So you should review various NLP concepts. All right, let's move to adversarial training. So for adversarial training, I have two things I want to do. I want to go over one of the problems that we have, and then I want to, sorry. So I think it's problem 5. I wrote it down. Oh yeah. So adversarial training, sort of at a high level, what are we trying to do? We're trying to fool a discriminator into believing that a picture that looks like a penguin is actually a picture of a truck, for instance, right? And what we want to do is, usually the vanilla flavor of this is, you start with an image and you want to try to minify it as little as possible and fool the discriminator as much as possible. And the discriminator here is just a classifier, right? Does that make sense? And so this is from last year's midterm, and it's, so I'm going to read it to you. For the adversarial perturbation method below, delta is the perturbation, J is the loss function, F theta is the classifier to be fooled, and Y hat is the target label. Yeah, LP is, this is LP norm. So the question is, if instead of wanting to fool one classifier, you want to fool n classifier, how do you modify this formula? All right, so I'll let you think about that for a minute. I'm going to start writing the answer, which is going to take me, oh, actually, maybe I can write it in text. Let's see how I do. Okay. So if you guys can't read LaTeX, let me know, and we can I can write some of the symbols. Essentially, what you want to do, and we actually accepted several answers for this, but they were all in the same flavor. So we'll go over it. So you still want to do an argument, and then this part doesn't change. So, okay, I'm just going to use D for delta. So the norm P of delta is the same, and the lambda for now I'll keep the same. And the main role of this is to make the delta, the amount that you need to change the image by, small. So you don't need to remove that. That's part of the normalization, and it's essentially LP normalization. You guys know about L2, L1 normalization. This is just LP regularization. All right, but what should change is that now we don't have a single classifier that we need to fool. We have several classifiers. So you need to add a sum from I equals, so from I equals 1 to n. Yeah, guys, bear with me. Of, and then here, each classifier is going to have a loss term, right? So here it's going to be f theta. So for theta, I'm just going to put a 0. No, okay, I'll just write theta. Theta. So here, this is where it's important to put the I of x plus delta. Okay, comma y star. I'm hearing bells. Is that people leaving, people entering, or is it people having questions?
People
All right.
entering usually.
Okay, cool.
Oh, so one person asked if the glue benchmark is the website that they posted. I believe that is the one, right?
So let's go to the glue benchmark.
Yeah.
You see, it's in my history.
Yep.
So if you type glue benchmark, you can see it.
Yep. So
And
it's exactly the one that the person posted in chat.
okay,
Mentioned.
cool. And if you look at the tasks, then you get a quick kind of description of each task, which is quite cool.
Right. And
but yeah, so then you can look at Superglue. Superglue essentially added a few more tasks like QA, like I was mentioning. But we didn't talk about it in the lecture, so you don't really need to worry about it. Just curiosity. Okay, so here I've written it. I hope most of you guys can understand it. Essentially, what I changed is that now instead of having a single term for a single classifier, we're trying to fool all the classifiers at once. Okay, so 2 errors that we saw last year that were common. Some people, oops, I'm gonna undo this. All right, redo. Cool. So some people had here, instead of y star 1, y star 2, y star 3. So that's wrong, because here what we're saying is we're still trying to target with a single target. So we're trying to fool all the classifiers with a single target. We're trying to make nth classifiers believe that this penguin picture, we want all of them to believe that it's a truck, right? We don't want one to believe it's a truck, one to believe it's a strawberry, one to believe something else. Okay, and the other error I saw that was common is to do a summation within J. But that doesn't make sense. You want to sum the loss of each individual classifier, not sum the inside the J. All right. Some things that would have been acceptable that you might think of is to put a 1 over n in front of the sum, or conversely, to multiply this lambda by n. But because lambda is a hyperparameter that we could have changed, we accepted whether you normalized or not by n. It was all fine. Okay. So then question B asked, assume J and F theta are differentiable. How would you optimize this formula? So if both the classifier and the loss itself is differentiable, then we would just use stochastic gradient methods to find the delta that we want. So I think you guys have done something very similar when you did the Google Deep Dream type of image. And if the C here says if J is not differentiable, what could you use to optimize this formula? And here I think the answer is you would have to use some kind of reinforce-based method. So you'd have to use some reinforcement learning. So basically it's like guess and check, right? And the C kind of gets to the point that sometimes you don't have access to the model, which means that here maybe F theta isn't differentiable because maybe it's what we call a black box attack, right? And in that case, you kind of have to do either you have to do guess and check, right? And then guess and check, then you can try to figure out what the next guess should be with reinforce, with reinforcement learning, or you have to do something a bit more clever. Okay, so that's what we were expecting. We were expecting you to mention either black box attack or reinforcement learning or something in the C part. And in the B part, it's just a white box attack, and you're just doing gradient descent. Okay, so yeah, I had noted here, let me just close the annotation. Okay. Oh, well, I have to erase it. All right, cool. So I had, that's good. All right. I had noted here that you should know about black box versus white box attacks. So hopefully you guys are all familiar with these concepts. Cool. All right, so let's move on to GANs. So GAN at a high level, generative adversarial networks. Essentially, you guys should all be familiar with the high level story. There is a generator, it takes in noise usually, and it tries to generate a sample that's supposed to look in distribution with some distribution that you have. So for instance, it could be a distribution of images. And then you have a discriminator that's a binary classifier that is trying to discriminate between real images and the images produced by the generator. The generator never sees the real images. The discriminator sees both. And essentially, they're trained in a kind of mini-max game where the generator is trying to fool the discriminator, and the discriminator is trying to, recognize the generator's pictures. Okay, so the best thing to do, I think, is to go over the problem because it asks some of the general questions. Okay, so I think it's this one. All right. So again, solves the following min-max optimization criterion where G is the generator and D is the discriminator. So essentially, this is the minimax game, right, where the discriminator is trying to minimize the loss, I think, and then this is the generator. It's trying to maximize its chance of fooling the discriminator. This is the 1 minus.
Oh, Philippe, sorry, because
Yeah.
there are a couple questions for your previous
All right.
question.
Cool.
So because you went to the next questions, I just want to make sure you take a look at those.
Okay. Yeah. Sorry, I hadn't seen. So Henry.
Yeah.
So Henry asks, I'm repeating the question for the recording. What is distribution of delta perturbation? So here there's no. I don't think there's a notion of the distribution of what delta should be. However, by saying that we're minimizing delta with norm p, we're essentially saying we want delta to be as small as possible in this norm p. So that looks kind of different depending on if you choose p equals 1 or p equals 2 or p equals 3, right? So here by if you choose norm 1, for instance, you might be saying, I want the perturbation to be sparse, right? So I want the image to be mostly completely unmodified and just in some places have peaks. If you choose a norm 2, you're saying something different. You want the norms themselves, the L squared norms to be small. Okay, so does that make sense? But we're not assuming anything about deltas. It's not following a Gaussian distribution or a Poisson distribution or something. Does that answer your question? Cool. The loss function depends on delta. Yeah, so you're trying to minimize delta. That's your objective. So what you're going to do if you're doing it with SGD is you're going to randomly initialize a delta, and then you're going to initialize it with 0 or with nothing, and then you're going to try to take gradient steps to try to maximize what's inside the argument. No, the loss doesn't have to be convex with stochastic gradient methods. So Henry is saying that the loss depends on delta, so the loss has to be convex, which means the delta distribution matters. So no, when you're doing stochastic gradient methods, because they're iterative, you don't need convexity. We're not trying to find the absolute optimal delta. We're going to just kind of iterate and try to find a delta that minimizes. Okay, cool. So the other question, Yifan asked, where can we find this last midterm? So yeah, I've realized that this midterm wasn't posted. We're going to post it probably today. Okay, cool.
But there is another question.
Okay, let me check. Sorry. What's the other question? Sorry.
So it says about for B, should it be gradient ascent instead of descent?
For B, let me check. So here, if it's I think it's still descent. You're trying to minimize the delta term, and you're trying to minimize the loss. So you're trying to make, so J here is often like cross entropy, right? And you're trying to minimize the cross entropy, which means you're trying to fool the discriminators or classifiers as much as possible, right? So I think in both cases, it's a minimization problem, right? And the only thing that when you have several classifiers, now you're trying to minimize it for all of them, not for one of them, right? So you're trying to minimize jointly, trying to fool all of them jointly. All right. Those are really good questions, guys. Cool. All right. So you can think about it more and we can kind of go over. I think I'm going to run out of time, but we can stay on a bit more if for those of you that have QAs. So let's go over GANs. Okay. So we kind of talked about it. So hopefully you know the high level of a GAN. So let's look at some of these questions. So suppose you perform adversarial training for a period of time and then fix D while continuing to train G. So you keep training the generator and you fix the discriminator. What do you expect the generator to do? Essentially, you know, if you fix the discriminator is not a human. It doesn't adapt to what the generator train if you don't keep training it. So essentially, the generator, what it's going to do is it's going to find just what we did before, adversarial examples that the discriminator is not good at finding, right? That because you fix the discriminator, so the generator is going to learn to cheat. It's going to say, hey, I've generated this image, and if I modify it a tiny bit, I fool the discriminator just a bit more, right? So it's going to essentially find these loopholes in the discriminator's space and learn to cheat in this way. All right. Second question, hopefully that makes sense. The second question is exactly the same but flipped, right? Suppose that you perform adversarial training for a period of time and then fix the generator while continuing to train the discriminator. What do you expect the discriminator to do? Essentially, you expect the discriminator to memorize everything the generator is capable of generating and be able to recognize it in this way, right? Because the generator doesn't have the ability to modify its behavior anymore. The discriminator is going to become better and better at discriminating, and essentially the generator is going to be discovered, right? It's going to be, it's not going to be able to fool the discriminator anymore. All right. These two questions are essential because they show you that these two models have to be trained jointly, right? You have to train one, then the other, then one, then the other, because they're playing this game, this dynamic game together, right? This is essential. You can't have a fixed discriminator. You can't have a fixed generator for too long because otherwise they learn to cheat off of each other. Does that make sense? Okay, so could the optimization be min-max instead of max-min? Yeah, I think so. I think you're just talking about the order in which you do these operations. So, Forrest, you're a GAN expert. So if I'm saying something wrong, you can.
Yeah, it really shouldn't matter because
Yeah.
When we do gradient descent, you typically do the min-max steps alternatively. So that so if you think in an epoch there might be with first G and then D, but then if you think across epochs, you're just doing it alternatively. So
it's essentially min-max, min-max, min-max.
Yeah,
so,
on the amortized fashion, it shouldn't matter which order it is. I believe so.
Cool. Make sense, Henry? Cool. Perfect. Let's move on. So the third question I thought was interesting. So suppose you alternate training. So now we're doing it correctly. And you're currently training the discriminator. Which of the following steps would be appropriate to stop? So it says the discriminator accuracy 0.5, 0.7, and 1.0. And this was a question that was a little bit poorly phrased, but we were trying to get you to think about, you know, how do you choose when you stop a single step? And essentially, the basics you should understand is that a discriminator accuracy of 0.5 means the discriminator has learned nothing because it's a binary classification, random chance is 0.5. So if the discriminator accuracy is 0.5, that means that essentially it has no clue and the generator is fooling it perfectly. On the other hand, if the discriminator accuracy is 1.0, that means it's like perfectly predicting you know, true data from like the generated data. And I think what we were going after, or what John was trying to get to here, is that this shouldn't happen because it means that most likely your discriminator has overfit and it has maybe memorized what the true data looks like. And so what you should be looking at is trying to find a discriminator that's around 0.7, 0.8, like some number that's largely above 0.5, but not exactly, you know, perfect predictions, right? So that, you know, essentially this difference between 0.5 and the accuracy of your discriminator is the signal that the generator is going to be able to leverage to try to make its generations better. All right.
Yeah, I just want to add a tiny note on here. So really technically, I believe when we graded this question, I think 0.5 is also acceptable with appropriate explanation. So what Philippe said is correct, and it's probably likely to happen if your discriminator accuracy is just 0.5. It's probably just likely not learn anything. But it could also be the case that it converges to 0.5 at the very end of the training, where your generator is just too good to generate something that's really realistic, that discriminator just, it's impossible with discriminator to learn anything. So 0.5 is actually the ideal case theoretically for, again, discriminator to achieve in the long run. But if you have to explain that in the exam last year to get the point 0.5, but practically what Philippe said is yes, typically you won't see that, or typically you'll see about 0.7, where basically your discriminator generator is trying to battle it out and get an equilibrium between them.
Yeah. Ideally, you end training with a discriminator at 0.5 and a really good generator. All right, so we have about 5 minutes of regular time, so it's actually pretty good to cover VAEs. And so I want to go over kind of quickly what VAEs are. And essentially, you know, AE stands for autoencoding. And autoencoding is something that we often have to do to compress information, right? So I have an image and I want to compress it, or I have some feature vector of size 1024 and I want to reduce it in dimension. And we want to do that with neural nets. So all of you should be familiar with PCA and how it works from linear algebra. But essentially, we want to do something a bit fancier than that with neural nets and see what we can achieve. And the thing is, this compression is all lossy, right? We're never going to achieve lossless compression. At least that's not the objective. And so I think actually I was looking at some of the material that we gave you about VAEs, and I think this figure, there's two figures here that are really good to understand the difference. Essentially, the first difference is the first thing you would try if you were doing autoencoding is to essentially, you know, have, if it's feed forward, you know, you would start with your input dimension, say 1024, and you would feed forward it to 512, feed forward it to 256, feed forward it to 128, and then make it bigger again. And that would be the encoder and the decoder, right? Just with fully connected layers. That's called an autoencoder. You then have, like, say, an L2 loss from the final layer to the first layer, and that's called the reconstruction loss. So that's the general autoencoder, and it's the first line here, right? So you have an encoding step that produces the Z. So here the Z that I mentioned had dimension 128, the X had dimension 1024 in my running example. And then you'd have, after the decoding, you'd recover D of Z, and you would have an L2 loss between D of Z and X, for instance. And it's variational, the V in VAE is for variational, and here what we're adding is a latent distribution. So the big difference is that instead of having these feed forwards, you're going to have the encoder produce parameters of a latent distribution. So very often we choose a Gaussian distribution, and essentially the encoder is in charge of choosing the mean and the standard deviation of this Gaussian. And then what you're going to do is you're going to sample from this distribution, right? And from that, you're going to have a decoder that's going to look very similar to the decoder in the AE case, that's going to reconstruct from this Z that you've sampled the input. Okay, so why would you do that? Well, you do that, sorry, let me show you this figure. You do that because you want points that are close in the latent space to be similar images, or similar in your actual space, right? And by doing that, by forcing the model to sample, And if you sample with a Gaussian, you're likely to sample things that are close together, close to the mean, right? You're going to enforce that, like, okay, like all the cars in my data set end up very close together, and all the, you know, trucks are going to be a little bit to the side of that, etc. Right? So it's a way of kind of enforcing here. They talk about it. They enforce continuity and completeness of the space, essentially. And what you have to do is, I mean, if you think about it and you forget about sigma here, if all the encoder did was produce mu of x, just a point, and mu of x is 128 dimensional, then that's just an that's just an AE that doesn't have to do anything with VAEs, right? So the other additional thing is that you're not going to just have a reconstruction loss. So this is the reconstruction loss here and here. You're also going to have like a, what do they call it? They call it a regularization term, which is basically saying that putting some constraint on what mu and sigma should look like. And that is usually a KL divergence between the mu and sigma that you produce and a standard Gaussian, normalized Gaussian. And the main reason you want to do that, I think is well explained here, is you don't want your space to look like this on the left here, because if you don't put any constraints on mu and sigma, like I said, you're going to end up with a regular autoencoder, right? Because space is infinite, so it's going to be able to put every single element very far away from each other. It's going to make the standard deviation small, and essentially, you know, you don't have continuity and you don't have completeness. So by forcing everything towards the center, right, that's what you're doing, and by forcing everything to have some standard deviation, that's the standard Gaussian process, you're forcing things to look like this, right? And that's good because now everything is going to be forced into this tight space, and with continuity, because you're sampling, you're going to force things that are close together in this tight space to be similar images, right? So that's basically what a VAE is. So things you should know is how the encoder works, how the decoder works, what are the names of the two losses, and sort of what do they look like, and what's the reasoning for VAEs. I really recommend this article. It's actually quite good at explaining you know, the difference between PCA autoencoders and variational autoencoders with really good graphics. It's in the homepage for the lecture. All right, so we're out of time. I'm gonna stay on for Q&A. We can stay on for 10 minutes. If you have somewhere to go, don't worry about it. It'll be posted afterwards. All right, cool. Thanks for listening. Let's see what the questions look like. All right, so Henry, you asked, how would the logits change here if we were taking argmax over a range of logits? Will the other logits be very small versus the target's class logits? Oh no, this is Ishan, sorry. Ishan, here the logits of what, sorry? I might have missed. Is this for the VAE or is this for the GAN? Okay, so let me look back at the GAN. Also for adversarial attacks. Okay, cool. So let's look back at that question, I think. So you're asking here, you guys should still be able to see my screen. You're saying, how would it look if this is not a classifier, right? So I think that's a good question. Essentially here, this J here that we gave you is a loss, right? And depending on what the model here is that you're trying to fool is, you're gonna have to change that loss. So here, because it's a classifier, J is most likely gonna be cross entropy. If F here was a regressor model, right? For instance, you were trying to estimate home prices, right? And you're trying to fool the model that predicts home prices, and that's a regression model. This would be an L2 loss, right? Does that answer your question? So you're saying, won't the logits change even for a classifier? So the logits are going to change. That's what you're counting on, right? So you, by adding this delta to each of the inputs, you're essentially changing the input, which is going to change the logits. And that's what you're trying to do, is you're trying to fool the model. Essentially, you move the logits all towards the target class that you want. Am I? Okay, cool. Perfect. Yeah. So let's see, Henry, you asked, is expectation if expectation is linear, why do we have two separate terms for GAN? Can we have one sum and one expectation with respect to X and Z outside of the sum? Okay, so let's look back at the formula. I think you're talking about the GAN formula. Sorry, guys. So if I look at the GAN formula, so you're saying why are these two things not? Why are these two things both in the expectation? I think this is like kind of the theoretical. I think this one is not necessarily an expectation. This is just kind of like what happens if you train in the long term. You're trying to minimize and maximize this thing. In practice, here you're sampling, right? So sampling is in an unbiased way will approach the expected value. And I think here you're also sampling real points from the real data distribution. So I think essentially this expectation here is just a symbol to signify that we're doing sampling. Does that answer your question? Would each expectation give an output in the block diagram? So which block diagram? Sorry. I'm not sure which block diagram we're talking about. So essentially, I mean, I can try to answer this question. Yeah, so the way it works, no, I'm not gonna Google this, but the way it works is you're gonna have a generator. I mean, I'm gonna simplify kind of like how it would work in one step. You're gonna have the generator. It's gonna you're gonna sample from this noise, right? So this noise here is, oh, okay, you understand the high level, but you don't understand the math. I think here the math is not exactly this is like what happens in the long term, and not necessarily what happens at every single training step. So this is, yeah, you can go ahead.
I could probably jump in. Yeah, so I think the expectation here is mostly for readability issues, just to make sure people understand that you're, because like the first part doesn't depend on Z, right? And the second part doesn't depend on X. Mm-hmm. Mm-hmm. So, but in practice, when you optimize the entire algorithm, you actually add them together anyways. So yeah, I can totally pull both of those guys out of it and do the min-max on that altogether. And in fact, that's what you're actually doing in the gradient descent. If you look at, let me pull this up. If you look at the, share. Can I share screen?
Yeah, let me let you share.
Yeah, if you look at the actual algorithm that they use for gradient descent, I mean, this is just equivalent to taking both the X and Z out of the expectations altogether. Mm-hmm. I believe so.
Yeah.
Yeah.
Yeah, so I think the best thing you could do is actually look at the algorithm itself. And then I think it'll be much clearer than I think the equation in the long term of what you're trying to maximize.
Yep.
Cool.
Yep.
Anybody else has questions? All right. So yeah, let us know. We'll be on Piazza. We have a few more office hours, so you can go to office hours and yeah, be ready on Monday. Cool. I hope this was useful, guys. It'll be on YouTube soon. Take care. All right.
Oh, are we done?
Yeah.
All right, I'll stop recording.
Yeah, I'm gonna close the meeting and it's